Okay, and the next classifier is naive-based classifier, which is quite simple, and it is based on the simple idea, and it can apply to some simple applications. Okay, again, for classification, what we want is posterior. Okay, so given x, okay, and what is the probability of class I? And that is a posterior. And when we have a two class, omega 1 and omega 2, then this one says the probability of class 1 given x. Okay, and then this one says probability of class 2 given x. So depending on these two values, if class 1 probability of class 1 is greater than class 2, then x can be classified into class 1. Okay, and based on the base rule, and we have likelihood, and we have prior, and we have partition function p of x. Or most equivalently, we can just focus on this likelihood times prior, because think about this one. We want to compare these two two probabilities. Then in this case, we have a likelihood and prior, and divided by p of x. And for this case, we have likelihood and prior, and divided by p of x. So we have the same kind of value here, and we can cancel, because we are just comparing these two probabilities. So since we have the same value, we can focus on this numerator. Okay, so this one is likelihood and this one is prior, and this prior might be given. Okay, so let's say we have a factory. Okay, and then in this factory, we want to classify on the conveyor belt. Then some product is coming, and we want to just classify this object. Is it class A? Is it class B? Okay. Then P of WI, the prior is just simply the probability of A and probability of B. Okay. In this conveyor belt, then how many A's we have usually and how many B's we have. Okay, so P of A can be simply the number of A over number of A plus number of B. And P of B can be simply number of B over number of A plus number of B. Something like this. Okay, so this prior can be given many times, but if this prior is not given, then simply we can use uniform distribution. So all these classes have the same kind of prior, okay, same kind of probability. In that case, we can just simply focus on the likelihood. Okay, so now the problem is in this likelihood, but the problem is it's hard to get the class conditional probability. It's hard to get this likelihood. So as always, in engineering, when the problem is too hard, then there are a couple of approaches. First, we can break the problem down into simple subproblems. Then we can solve the simple subproblems, and then we can merge the results. Okay, that's one way. Another way, many times, okay, we use approximation. So we approximate the problems to make it simple, and we solve that approximated problem. And if this approximation is reasonable, then our solution is reasonable solution. But if this approximation is too much, then our solution is not making any sense, right? But in this case, naive-based classifier take another assumption. Okay, so let's see what kind of assumption it has. Okay, original problem is this one. We have to we have to estimate this probability, which means given this class and we have data x, then what is the probability? Probability of x given class. Then it's hard. Then to make it simple, we take one assumption, which is the features are class conditionally independent. Okay, so if the class is given, so we know this class, then the feature 1 and feature 2, this one is one vector. Okay, so this one is the dimensions. All these dimensions are independent. Okay, usually that's not the case. Usually, but when the class is given, class is conditioned. So under this condition, these dimensions are independent. That's the assumption of naive-Bayes classifier. Sometimes this assumption is good. It makes sense, but sometimes it doesn't make any sense. If it doesn't make any sense, then the naive-Bayes classifier is not working at all. Okay, so if you apply this naive-Bayes classifier to MNIST data classification, it doesn't work. And for MNIST, if we apply the KNN, then it works greatly. Okay, it's not the best algorithm for MNIST, but KNN works quite well. But naive-Bayes classifier doesn't work because, think about this one. We have one image here. Then we know what kind of class it is. Okay, let's say this one is, we have some number here. And then if it is from class 3, then even when we know the class, then are these pixels independent each other? No, that's not the case usually. Think about this one. We have another 3 here. Look at this one. If this cell has something, then probably this cell has something, right? This cell has something, and this cell has line, and then this one has line too. Okay, if this cell has a line here, then this cell has line. So there is correlation, there is dependence between the pixels. Okay, so this assumption doesn't work in this case. That's why when we apply naive-Bayes classifier to MNIST classification, it doesn't work at all. But sometimes this assumption makes sense. Okay, then naive-Bayes classifier can work perfectly. So you have to understand what kind of problem you have. That's why we are studying all these different kind of classification algorithms and principles and characteristics. Okay. So assuming that the features are class conditionally independent. Okay, if this assumption is correct, then let's drive the solution. Okay, so this one can be decomposed to this one. Okay, because we assume that all these features are independent, so we can multiply. This one is probability of the feature in D dimension given class I. And then we multiply these probabilities from 1 to D. Okay, because these are independent. Good. Okay, don't get confused with this and this. Okay, so when we multiply probability of xd given omega I, that's not that this. Okay, usually in general the features are not independent. Okay, features are dependent if we don't have this condition. Without Okay, look at this one. We're just talking about the probability of dimension D. Most of the time, this is not. Okay. But if we put this condition, then sometimes, yes, this might be right. This is not correct all the time. This might be correct sometimes because of these conditions. Okay, and compared to this one, when we have a lot of data samples, x means x1 to xn, okay. When we have n samples, probability of n samples will be product of p of xi. Okay, this is usually what we assume in pattern recognitions. Data samples are IID, okay, independent. So in most cases, okay, most of the time, this is correct. This is not correct whatsoever. All the time, this is not correct. This is all the time, most of the time, this is correct. This one, sometimes this is correct. Sometimes not correct. Okay, because the reason why I explain these three different things at the same slide is that many students are confused with these three things. Okay, they are different stories, okay? And finally assign x to class omega I, which maximizes this one. Okay, so this one is actually about posterior without p of x, because as I said, we don't care this p of x at this moment. So this one is actually posterior, and this one is given like this, and this part can be decomposed into the features. Okay, then in training, what should we do? We have to learn this probability distribution for all dimensions, and this one. And this one can be simple, just to count the number of samples in each class. Okay, that's simple. And what about this one? So we are talking about just one scalar, and you can use Gaussian distribution if you want. Okay, then, or if you think this feature is really complicated, then you can use a mix of Gaussian for this. For one dimension, you can use mix of Gaussian. But anyway, you can have one model for this feature dimension, and then you can estimate the parameters, and that's it. And then once you are done with this training, and then given a new sample, then we can actually calculate this one. Actually, we can calculate this one given a new sample. Then basically we can compare. If we have two classes, then we can compare this one and p of x omega 2, p omega 2. Okay, so given new sample x, then we can compare this one and this one. Then we can classify depending on these values. Okay, as I said, class conditional independence might be too strong assumptions. So you have to know what you're doing when you use naive-based classifier.